Okay, we're going to get back to the matrix inverse now. This is still chapter 4. We just did determinants. Now we're going to do the matrix inverse. And a lot of the things about the inverse we bring up in pieces because it's kind of complicated. First, we defined what it was and some of the properties of it. And then we came up with at least one way to calculate it. So let me first review some of that stuff. First, it was a definition. Well, it only exists for a square matrix, the way we define it. And it has this property where this a to the minus 1 means the inverse of the matrix A. It says if you multiply the original matrix A either on the left or the right by the inverse, you get the identity, and the inverse is unique. Not all square matrices have an inverse, and I think we derived the test for those. One is if the rank of A is n, where A is n by n. The other is the determinant not equal 0. If the rank is less than full rank, meaning less than n, or if the determinant does equal 0, you've got a singular matrix, which means it is not invertible. There is no inverse. Some of the properties, the inverse of an inverse, the original matrix, the inverse of a product is the product of the inverses, but in reverse order. The inverse of a transpose is a transpose of the inverse. And this one's kind of nice. You can solve AX equals B if A has an inverse by this matrix multiplication. It's actually no more computational convenient than Gaussian elimination, but if somebody gives you the inverse, it's very easy. And this is a unique solution because the inverse is unique. So if your matrix A is full rank, you're going to get a unique answer. And that method we had of calculating an inverse, we use Gaussian elimination. And what you end up you augment the matrix with the identity matrix and do Gauss-Jordan elimination, and you'll end up with this EA. E captures all the row operations. If what you end up with on the left side here is the identity, that means what's on the right side is the inverse. If you don't get an identity over here, then it doesn't have an inverse. So now let's get into another way to compute an inverse. First, we got to talk about the adjoint matrix. It's the transpose of the matrix of cofactors. We already went through cofactors when we talked about determinants. If A is just 1 by 1, the adjoint is defined to be 1. For n equals 2, if you just take this definition, well, if it's only 2 by 2, the cofactors are just the other elements. I'm not going to go through all this. You get a very simple sort of formula for a 2 by 2. You swap the main diagonals and change the signs of the off diagonals. That is worth memorizing. It's easy to find the adjoint of a 2 by 2. Swap the main diagonals, change the signs on the off diagonals. 3 by 3, you're stuck with a lot of computation. If you've got a 3 by 3, you've got 9 cofactors you've got to compute. Each one being a 2 by 2 determinant. The 1 cofactor for the 1 term is going to be this guy. Each cofactor has a little 2 by 2 determinant. You've got to calculate all those. The adjoint, though, is the transpose of those cofactors. So here's the matrix of the cofactors. They each correspond to the original matrix. 1, 1, 1, 2 term, 1, 3 term, same subscripts as the original matrix. But the adjoint is the transpose of it. So you're going to have the 1, 1, 1, 2, 1, 3 as the first column, etc. That's what an adjoint is. Why does it work? Well, let's look. Or why do we want to compute such a thing? I should say. What if we multiply the original matrix by that adjoint matrix on the right? You get this. Trust me on that. And if you look at that thing, these main diagonal terms, those were the formulas for a determinant, the determinant of the original matrix A. The off diagonal terms, trust me on this, it's the way that matrix multiplication works out, these multiplications work out, is you'll end up with matrices that have duplicate rows. So those things, those determinants become all zeros. These are like all determinants of some matrix, but the main diagonal is the determinant of A. Off diagonals are the determinants of matrices that have duplicate rows. So they're going to be zeros. So if you multiply A times that adjoint, you get the determinant of A, which means we now have a formula for the inverse. It's that adjoint matrix divided by the determinant of A. There's a formula. And we'll do some more examples in another video. We're already running over.